I want to get these three questions out the way. These are 8, 19, and 20 from your section on trig graphs. And then we're going to jump right into section 5.4. And I'll tell you right up front, 5.4 is going to be an awful lot of note taking, right? We're just going to be writing stuff down and copying pictures. So, be prepared for that. So in this one here, it's question 8. The reason I'm putting this one in is because it talks about frequency, and that we haven't really covered yet, but there's not an awful lot of questions involving frequency. So here we go. So a tuning fork is, you hit it and it vibrates, and the velocity that it vibrates at time t is given by this rather ugly trig function. And we're being asked to find the period and the frequency. Now, the period is 2 pi divided by b. And in our world, this guy is called a, and the coefficient, this whole thing here, is called b. So it's going to be 2 pi divided by 910 pi. You can cancel the pi's and cancel that down, and I believe you get 1 over 4. Is that 4? Sorry, that question's 8. There we go. 1 over 405. And that's it. Rather small period. Can you imagine that if you drew it would be a very ziggy-zag, right? A very compacted sine function, right? Now, they talk about the frequency. The frequency is how many cycles you get in a second. And the formula for that is simply just 1 over the period. So that's how you get the frequency. It's 1 divided by the period. And that is 405 cycles per second. So that's what you would be calling, sound like 400 hertz. Hertz just means cycles per second. So the frequency of sound might be 400, it might be 4,000. 4,000 would be so high pitched it would probably hurt your ears if you could hear it, right? And 400 is a very small number. Useless piece of information. Do you know that whales communicate by sound? Do you also know that whales communicate very often by really low frequency sounds? And the advantage of a low frequency sound is that in the water, because that's where they make the sound, right? It can travel like 20 miles. That means one whale can talk to another whale 20 miles away, right? If you look at some other animals like porpoises, don't they do high-pitched squeaks and clicks? So their frequency is much higher. And that also means they don't travel as far. But dolphins go about in little packs, so that probably doesn't matter. Whales tend to go around in much smaller groups. So I just told you some stuff that you don't need to know, but what you do need to know is to get the frequency of a trig function, it's 1 over its period. And we're done. Now, this one dead easy because I've given you the answer. You have to graph it. And that's what Desmos does. 0 to 2 pi, you've got it. So I'm now going to move over and, this one here, question 20, I'm going to do that on Desmos as well. You've been asked to find the maximum and minimum value of this expression using a calculator. To me, calculator or Desmos are equivalent. So got the guy set up. Let's do the absolute value one, show you what that looks like. Here we go. If you click on this guy and do that fella, you can type in y equals, in this case it's 3 absolute value, which is that button, and inside you put sin x. I should be able to click out and press, oh, it's already done. Do you see that's the guy? They're doing it from 0 to 2 pi. So if I wanted to do it only in a a small range. Curly bracket, 0 less than or equal to x, less than or equal to 2 pi, and colon. And notice you don't write y equals. You got it. There. There. Can you see 0 to 2 pi? Nothing big going on here. Now, the last question is also from 0 to 2 pi. So I'm going to use the first bit up to the colon. And the function is y equals x take away 2 sine of x. And I'll shrink it back a little bit. There we go. Now, maybe slide it over a little bit down, make it a touch bigger. There. So we're being asked to find the maximum and minimum value of this function. If I click on, I think about there, would you agree that's the biggest answer? 6.968. Does that seem reasonable? The y value, 6.968. And if I click on that one down there, do you see it's negative 0.685? So in the question that we are doing, I better put those numbers down to remind them, 6968, and the other one was negative 0.685. There you go. And they've got 697, so they rounded it off, which is fine. And they rounded that one off. So there is, you see the two answers that I had? That's it. Any questions about those last tidy up, guys? Anything seems pretty easy. Calculator does 2 of them. And the other one is just remember that frequency is 1 over the period. Right. Now,
the last graph you showed,
yes.
How did you get the x coordinates be in terms of pi?
How did I get, say that again, the x?
Because on the point you have highlighted, it's 5 pi over 3. How did you get it in that form?
Oh, I just clicked on it and it told me that. I didn't do anything. It's just what I clicked on. See, if I clicked on here, you see I was just weird decimals. If I clicked on here, it's weird decimals. Yeah, everybody's a weird decimal except that one. So I didn't need to do anything. All I did is click as best I could on the top of the hill and see down here. I did that one. Does that answer your question?
Yeah.
Yeah. It's not like you make it do 5/3. If it's 5/3, it'll tell you, and if it's not, it'll tell you a decimal. Let's get this show on the road because I promised you, or threatened you, I'm not quite sure which, that you're going to have a lot of notes. And that's for 5.4, which is called More Trig Graphs. Very unimaginative title. Here we go. We know that there are 6 trig ratios. There are 6 trig functions as well. And each one of them has its own graph. We've spent most of our time on 1 and 2, right? That was the section 5.3. We're going to now spend the rest of our time on the last 4. So we're going to look at what does the graph of tan x look like, cosecant, secant, and finally cotangent. All of these are going to be done with the help of decimals. Right, that's the easiest way to do it. So, with this guy over here. And for each of these graphs, I'm going to find the period and the range, and I'm going to graph them, right? So only for completeness sake, I'm going to do sine x again. Now, I don't need Desmos for question sine x, and I'm only going to draw one cycle. So in other words, I'm going to do 0, there's pi, and 2 pi. And for consistency, I'm going to do them all in that range. So if you're doing the sine function, kind of goes up like that, right? And it goes down like that. And we know this guy is 1, and we'll know this guy is -1. So isn't that what the graph of sine x looks like? We've done plenty of those guys. Right, that's what it looks like. If you want to find the period of sine x, its period is 2 pi. Would you agree? If it's just sine x, from start to finish, till it repeats itself, it's 2 pi. Now, if I ask you to find what the range is, remember what the range is. The range is always about the y values, right? And in this case, the range is from -1 to 1. Would you agree? That's pretty obvious as well. You can see it on the diagram. So the range of y's. I'm not putting the domain in, and the reason why I'm not going to put the domain is, can you imagine that the domain, the usable value of x, are all real numbers, right? We don't need to do that. So again, for completeness sake, we're going to do cosine x. So this set of notes is going to be like, if you do good versions of them, then couldn't this just be your go-to page when you want to remember what does a tan look like? You know, what does a secant look like? You know, what kind of range do they have? You know, questions like that. You could go to these pieces of paper and just look at them and say, ah, yeah, gotcha. Now, we're going to do 0, we're going to do pi, and we're going to do 2 pi, just fine. And I'm going to start here 1, and finish down here at -1. Okay, there. We'll mark here, mark here, mark here. Just trying to give myself a chance of drawing a reasonably nice looking. Oh, am I good or am I good? Oh, come on. That is for me, that's pretty clean. That is pretty cool. Right. You know, normally when I draw them, I make the top one high and the little one not quite as high, or one of them's fatter and the other, you know, there's a whole load of things kind of wrong with the thing. I guess I should write down, although it's pretty obvious what these are, but just for completeness sake. Okay, the only two things.
Are all the graphs going to be on the same plane, 1 and -1? And 55?
Oh, you mean the other 4?
Yeah.
No. But we'll find out what they are. That they're not going to be from -1 to 1. That would be really nice if they were, but they're not. And the period of this thing is 2 pi, and its range is also from -1 to 1, right? Agreed? -1 to 1. That's those two guys over with. So number 3 in my list of trig functions is now going to be tan x. And I'm going to, oops, I'm going to put in 0, pi upon 2, pi, oops, 3/2 pi, 2 pi, right? I'm going to do from 0 to 2 pi like everybody else. And I'm now going to go and get Desmos to draw it for us. So I'm going to leave here. I'm going to go into Desmos. I'm going to keep that 0 to 2 pi thing, because that's kind of helpful. And I'm going to go tangent of x. And don't be worried about the weird looking thing. I'm going to move it along and move it. I really should change this window here. So I want this to be from 0 to 2 pi. So I'm going to have to tweak it quite a bit. And I want the y values also to be changed a little bit. So I'm just basically figuring out scales that I think show you all the features of the tangent function. Okay, let's click off that, click off that. Right, now, if I zoom back a little bit, there we go. And I move this over here. Do you see that the tangent function has a very weird shape? Now, I'm going to be drawing this guy in a few seconds, but the first feature I'm going to use is, do you notice that at this point here, round about 1.5, right? Isn't there a vertical asymptote? You see that? And then later on, round about, I don't know, about 4.8-ish, do you see there's another vertical asymptote? Now, keep that picture in your mind so that when I draw this one, you can maybe see what the heck's going on. At pi over 2, that's the exact value where that vertical asymptote was. And that other one that I mentioned, its exact value is at 3 over 2 pi. And you can actually find those two guys. If you had your unit circle on you, wouldn't that be the two guys where you ended up dividing by 0? Right? So that's why that happens. Now, the shape that we got, right, well, it started off here and it went vertically upwards. And then it went here and it went vertically downwards. Do you see that shape? Basically, it's a, well, it's like a little vertical asymptote, isn't it? Now, it then went back up here, and then it went to there. And that pattern continues in both directions for infinity, as all trig functions do, don't they? Right? There's a basic building block and then they repeat themselves. Now, what might not be so obvious here is the period of a tangent function. So from 0 to where does it repeat itself? Well, I got a piece of paper that'll work, I think. Do you see that little shape there? That goes up and goes down one, right? Isn't that repeated there? So this shape, doesn't it repeat itself from 0 to pi? Do you see that its period is not 2 pi? Its period is only pi. Are you comfortable with that? Does that make sense to you? That this shape repeats itself by only using that as its building block, right? One up and one down, then one up again and one down, one up again, one down. Now the range, well, the range in this guy is up there, right? Down there. Isn't that basically everything? The biggest y value is plus infinity, right? And going down the way, the smallest is negative. So the range is essentially all real numbers. Do you see that's not 1 to minus 1, as someone said just earlier today? Do you notice that it goes up to and down to plus and minus infinity? And from Calc 1, it has vertical asymptotes at x equals pi upon 2, x equals 3 halves pi, x equals ... forever. Doesn't it have an infinite number of vertical asymptotes? Because if you keep repeating this process, won't you get another vertical asymptote, then another? And if you go this way, won't you get a lot more? Quite a weird function, the tangent, isn't it? It doesn't, it's not nice, smooth sine or cosine. I mean, it's quite different in shape. It has a different period. It's pi, not 2 pi. It has a different range. and it has vertical asymptotes like none of the other side. I mean, all in all, quite different, isn't it? Are we good with the tangent? Are you comfortable with shape and all this, all the little details that we've got? So I'm going to move that guy over to my little list, and we'll look at number 4. And we're going to look at cosecant x. Cosecant x, by the way, isn't it the same thing as 1 over the sine of x? Right? Remember, it's reciprocal. Now, I don't know if this is going to work, so that's why I put my backup plan. I'm going to do Desmos, and I'm going to sketch cosecant x, and I'm going to try it as cosecant x. And the good news is it understands CSC, right? Because if it didn't, I was going to do 1 over sine, sine x. For instance, see if you do your TI-84 calculator, won't you have to type in y equals 1 over sine x if you wanted to do a cosecant, right? But thankfully, this guy is much nicer. So I'll move it up. And I'm going to change the y values this time. And I'm going to change these y values to, I don't know, let's find out. -10 to 10. Yeah, that works. Yeah, that'll work. I'll use that. Right in the middle here, right where my mouse pointer is going on down. Do you see another one of those vertical asymptotes?
Yeah, it's at pi, right?
And it is at pi. Could you make an estimate? It's about 3.1 is, and that's what pi is, right?
Yeah.
About 3.1. So that's the guy. Hold that thought, and I'm now going to try and draw essentially the same thing. And then we'll add some information about the guy, right? So there's 0, there's pi upon 2, there's pi, there's 3/2 pi, and there's 2 pi, right? And right at pi, there was a vertical asymptote. And, well, I don't care. Blue will do. Okay, can I change this? There, make that 1. Make that -1. It's a little bit easier to see. And it looked like this. And then here, it looked like this. Now, what I haven't put in yet is that there's another vertical asymptote here. And there's another vertical asymptote here. So basically, isn't the cosecant x a happy face and a sad face? Right? Happy face, sad face. Now, what would go here? Another happy face, another sad face. Can you imagine? Happy face, sad face, happy face, sad face. Right? That's the building block. That's the shape that repeats itself forever if you do a cosecant x. Now, the period. 1 pi or 2 pi? Which is it?
2 pi.
Agreed. Now, the range is a little bit messy. Isn't the range 1 or bigger and -1 or less? Would you agree that's the range of the y's? There's a band of nothingness that the cosecant is never equal to, right? You'll never get a cosecant equal to 1/2, for instance, right? That can never happen, right? Do you see the lowest they get to 1 and then anything bigger? Or on this side, -1 or anything smaller. So when we do that,
Y asymptote.
No, there isn't a horizontal asymptote, but there is a band of y values that you never equal. And that's going to show up in the range because it's going to be negative infinity to 1, and then nothing much in the middle. And then it starts off at negative 1 and nice. I had it right the first time. Don't know why I was rubbing the thing off. I'll rewrite it again. You're doing negative infinity to 1, and then you're doing 1 to infinity, which is what I tried to write the first time and talked myself out of it. And we have vertical asymptotes at x equals pi. Also at 2 pi and at 3 pi and forever. Aren't they going to be an infinite number of them? If you think about it, it makes sense why there's a vertical asymptote at x equals pi. Because isn't the sine of pi 0? And won't 1 over 0 cause vertical asymptotes? Doesn't that make sense? So where the sine is 0 is going to be where the cosecant x has a vertical asymptote, right? So the sine has a 0, the sine is 0 when you have 0 radians, pi radians, 2 pi, 10 pi, and so on. And we go with that guy. Now,
So just to clarify, so it can equal 1 and negative 1?
say that again.
It will equal 1 and negative 1?
Yes, it will reach 1. That value there exists, right? You can get a cosecant equal to 1, and you can have a cosecant equal to negative 1, right? And lots of other numbers, right? Bigger or smaller than that. What you cannot get is a cosecant equal to any number in this little gap, right? Between here and here, right? There, can you see? There is no cosecant function. So you can never get a cosecant equal to half or to 0.9 or to negative 0.8, right? Those guys won't exist, right? It's a bit like me saying the alternate. If I said to you, the sine of x equals 10, aren't you going to say to me, no, it isn't? You can never get the sine of x equal to 10. Isn't the biggest sine value 1? And the smallest value you can get from a sine is negative 1, right? So there's a kind of restriction on what a function can be equal to, which is essentially what the range tells you. It tells you what a sine, a cosine, or in this case, a cosecant can be equal to. And it can only be equal to numbers in this range. We good?
Thank you.
Right. Moving on. We only have 2 more to do, and then we get into the details. Let's do a sketch of that guy. And we know is that fella. I'm going to be taking it into Desmos in a few moments from now. I want you to see if you can make a prediction of what it might look like. Shouldn't it look similar to, but not the same as cosecant? Just like cosine is similar to, but not exactly the same thing, right? Isn't the secant and cosecant kind of, if you take one and shift it a little bit, you get the other, right? Remember that? The sine and cosine look like you've shifted. So what do you think a secant might look like?
Well, we know that the vertical asymptotes would be at pi over 2 and then 3 pi over 2.
I like your thinking. And that's because at those points, the cosine is 0. So let's put in what you just said, because I like it and it's correct. We're going to do this in Desmos in a minute. Right. Now, between 0 and pi upon 2, isn't the cosine a positive number? And the biggest number you're going to get is 1. So I'm going to make a prediction that it's going to look like that. And at pi, you're going to get -1. And I'm going to make a prediction that it looks like that. What do you think it's going to look like in this little piece over here?
You reverse the first line, so yeah, that.
Something that looks like that. If you took this shape and slid it that way, wouldn't you end up with this one? Or if you took this shape and slid it that way, wouldn't you end up with this one? You see that they're very similar in shapes. Well, let's verify that what we predict is in fact what it ends up being. So we're going to be doing secant x here. Does that look good? Right? Happy? I mean, if I shrink it this way, yeah. Does it look a little bit more or less like we talked about? Try to shrink it a bit more. How about that? Yeah. Does that look better? Does that look closer to what we drew? Right. It worked. We got it. So we are going to be looking at the period, and we're going to be looking at the range. Okay. I just realized I might not be on the whiteboard. There we go. We're going to look at the period, and we're going to look at the range. What do you think the connection between the period and the range for a cosecant and the period and the range for a secant? Do you think there's going to be any connection?
Going to be the same.
They're going to be the same. Does that make sense? That the period is 2 pi, right, from start to finish, right? If you repeated that shape, right, if you took this, made transfer and slid it over here, wouldn't you get the rest of the happy face and another sad face, the rest of the happy face, another sad face? If you went this way, wouldn't you get the rest of the happy face, then a sad face, right? The rest of the happy face and then a sad face, right? This here is the building block shape, and it's from 0 to 2 pi, and we call that distance to period. And the range, right, 1 all the way up, and -1 and all the way down, right? Isn't that the range that of values that the secant can take?
You just forgot to put the negative behind the 1.
I forgot to put
First bracket.
first bracket.
The first one. So -1 or -infinity.
Oh, did you all catch that deliberate mistake?
I did,
Does-
but I wasn't
yes,
sure if it
did
was a mistake or not,
anybody-
so I was going to ask, but yes, first.
Does anybody here actually believe that that was a deliberate mistake? You know, that was just a mistake, right? I just missed it. Welcome. I like that because that means you know what the heck's going on. I like it.
It should be changed on the coseconds range also.
That I didn't notice at all, but yes. Although I'm pretty sure I said -1, I'm pretty sure I said that, I just didn't write it. You should write it, but I didn't. Well, it looks like we've only got one more of these guys to do, and we're kind of over that initial writing lots of notes down. The last one we're going to do is the cotangent of x, and the cotangent has the property that it is the reciprocal of the tangent, right? So it's the same thing as 1 over the tangent. So I'm going to see if I can find my tangent guy, because we might be able to use him to predict what the shape would look like. And then we'll put it into Desmos. and see what happens. And so I'm going to go 0, pi upon 2, pi, 3/2 pi, and 2 pi. Have you noticed that when you draw any of the trig functions, aren't these the key points where things happen, right? Where something vertical asymptote, or the bottom of a happy face, or the top, or whatever it might be. And so these are key places. Now, if you look at the tangent function, it has this vertical asymptote going up and down. Now, when the tangent is 0, won't the cotangent be 1/0, which means that it's going to have a vertical asymptote here. At pi, it's going to have a vertical asymptote. And 2 pi, right, because the tangent is 0 there, and 1/0 is going to cause a vertical asymptote to happen. Right? Are you happy about how I made the prediction on 3 vertical asymptotes by knowing that the tangent is 0 at these 3 places? Because if the tangent is 0, won't the cotangent, which is 1/0, be at a vertical asymptote? Now, what's going to happen at pi upon 4, or pi upon 2, I should say, right? At pi upon 2, right? Isn't the answer infinitely big? On this side, isn't it infinitely big and positive? So what do you get when you take 1 and divide it by infinity? What kind of answer does that come out to be? 1 divided by infinity, and it's a number. 1 over something infinitely large.
That would still be infinity, right?
1/0 gets you infinity, right? It gets you a vertical asymptote. 1/infinity doesn't. 1/1,000,000,000, right? 1/1,000,000,000. 1 over the American debt, right?
It's a very small number.
In fact, 0. So I'm going to have an x-intercept there and an x-intercept there. And this is positive, so that's going to be positive. And this is negative, so that's going to be negative. And this is positive, so that's going to be positive. And this is negative, so that's going to be negative. So that's my prediction for the cotangent of x. Right. We should be able to just put it into Desmos, but I thought it was interesting to try and predict it. Would you agree that looks pretty much like what I just drew? So it's verified. So for completeness sake, we should add in what the period is, what the range is, and lastly, where you will find vertical asymptotes. Okay. What interval do you need for this shape to repeat itself? So what's the period?
Pi.
Great. Would you agree that's the building block, isn't it? And then you repeat it. See it? 0 to pi. Which is maybe not a surprise, isn't it the same for the tangent? Would you agree that it goes all the way up to plus and minus infinity? So the range is everybody. Exactly the same thing for the tangent. Now the vertical asymptotes happen at x equals 0, x equals pi, x equals 2 pi, and so on, right? Vertical asymptote at pi, vertical asymptote at 2 pi, and so on and so forth. Are we good so far? And that is the basic shape for all 6 trig functions.